So it's my pleasure to present to you today some of the work that we've been doing at Genentech. How do I? Oh, there, okay. So today I'm going to discuss some of the work that we've been doing to try to help our project teams and chemists search and mine some of our project team documents. We already have solutions in place to capture and mine experimental data, calculated properties, the results of DMPK models in Oracle with Schrodinger's Syrah, Dotmatics's Vortex, and other internal tools. The key thing that we're interested here in this project is trying to understand whether or not we can mine these documents, the content of these documents, to help project teams understand how to overcome certain problems that they may be facing, such as solubility, hERG, time-dependent inhibition, clearance. So the first part of the project is to implement a Techspace Searching application based on Apache SOLR. I'll discuss this application briefly and show why this motivated us to evaluate ChemAxon's documented database. And then I will conclude with a summary of our observations as well as some future directions. At Genentech, as well as many other biotech and pharmaceutical companies, a therapeutic project team will generate many documents during the course of a project. Some of these documents include project team reviews, target candidate profiles, regular medicinal chemistry design sessions. There are also many different presentations and reports that come from other groups. For example, the HTS or the fragment screen, in vivo reports for safety, efficacy, PK, PD. At Genentech, we have regular structure-based drug design with the medicinal chemists, the computational chemists, as well as the structural biologists. They do a lot of modeling, they do a lot of docking, and often this information is captured in a presentation. And finally, we have diagnostics and biomarker reports. So at the very least, a project team should be able to find their documents to understand key experiments that have driven the project in the directions it's going. They need to find the documents so that they can publish papers or file patents. But these documents contain a lot of key discoveries, some techniques for overcoming some of the problems that they've had, as well as the best practices of the project team. And so the question that we ask is, can a project team today make use of the information in these documents and learn from what a project team has done in the past? And to really illustrate that, I want to go back up to the first type of document here, which is the project team reviews. At Genentech, periodically, a project team will meet with scientists, chemists, as well as the senior leadership and provide an update on the progress since the last review, the current state of the project, as well as any hurdles or obstacles that the project team is facing. These presentations occur periodically, so by looking at the series of presentations, you can learn how the project progressed, what issues they faced, and how they actually solved them. So that is the goal of this project. Unlike many of the previous presentations where they were dealing with patent documents, most of the documents that we are looking at were generated in-house, so we have a lot of control and we can actually specify what they should include. For example, chemical structures are represented by either embedded ChemDraw or by corporate identifiers. So in the past, it was actually very difficult to find project team documents, let alone be able to search for them or to mine them. Project teams found their own ways of storing their documents. They used a variety of different tools, including LiveLink, an internally developed application, as well as the file system, which didn't lead to searching at all. It was around this time that Genentech made a strategic decision to adopt the Google applications for mail, calendar, and instant messaging. And along with that, we got Google Drive. So we evaluated Google Drive, and we found that there were a number of important features that it has. First of all, it's actually very easy to use. Secondly, there are no workflow functionality required. For example, there's no document approval, no check-in process, no checkout process. So this made it very easy for the scientist and the chemist to use. It's also readily accessible by our partners and CROs. Each one of our projects at Genentech has a CRO attached to it, and many of them also have, in addition to a CRO, a partner. So we have many three-way collaborations. And so having a place where we can exchange all of this information was very important. It also has versioning and simultaneously editing of Google native documents. But very importantly, much of the administration of the project team documents is in the hands of the project teams themselves. They can easily control the organization and the structure of the documents, and they can also easily control the access permissions by adding the email address of a user or of an individual or a distribution list. So today we have about 84,000 project team documents that are in Google Drive. There are a couple shortcomings of this solution. First of all, and I'll come to the reason for this later, there is no wildcard or substring search. But ironically, I find this very ironic, Google being a search company, our users have a very difficult time finding the documents. And so this was the motivation for us to write our own search engine on top of Google Documents. So as most of you know, SOLR is part of the open source enterprise search platform from the Apache Lucene project. It has full text searching, faceted searching to limit your results, hit highlighting, and it also supports a wildcard, regular expression, proximity, and fuzzy searching. So there's a lot of search power behind SOLR Lucene. And thanks to our corporate IT group, documents from select folders on Google Drive are copied to the file system inside our firewall every 30 minutes. And so this is the collection that we're going to be searching with SOLR. One requirement, which was difficult to resolve, was that the project teams wanted to ensure that we honored the permissions set up within their files. And as most of you know, SOLR has no means in itself for authorization of access to documents. So we took two different approaches to this. First of all, we locked down the servers so few people could log into the servers where the SOLR indexes were stored. And we also limited by the IP address which computers or which applications could actually connect to SOLR. And finally, we consulted with LucidWorks, who implemented LDAP integration to provide the authorization. So this is a screenshot of our main application within Genentech. It's a web-based application. We use many commercial products such as Syrah, Vortex, the Symix ELN, Mo, and PyMol. But the core of the informatics system at Genentech is based on this web application. There are many different applications. For example, compound registration is a very robust with rigidly enforced business rules to register compounds. Even more than that, if a chemist registers a valid structure but then later finds out through analytical data that they registered the wrong molecule, they can go in and edit the structure. Over here is part of our reporting. So this is a form-based reporting system where the users can actually configure their own form-based report. A very typical one is where they, what we call the compound summary component, where the structure is in the column header, and then there are assay results highlighted with the traffic light, green, amber, red colors. This can show multiple structures going across the different columns, and all of this can be exported directly into PowerPoint with embedded ChemDraw. And so this is a tool that really helps the project teams generate PowerPoint presentations by querying the database and getting the data. There's also connections to KNIME so that we can perform docking as well as supervise match pair analysis. There's also a number of request systems that help us manage the cycle times of the project so we can request an assay and understand when the results will get back to minimize the cycle time. So in this example, I selected what is known as the SMDD document search project or application, which stands for small molecule drug discovery document search. And so here's the keyword search. You can type any search term here, the document type, the owner, the folder name, the part of the title of the document, and you can search. There's also a Chrome extension, which gives you a little extension right up here. So no matter where you are in your browser, you can go to the search page and search for your document. It also supports all of the SOLR query features in this text area. So if you're a power user, you can implement very complex searching across all of the documents, and we have documentation for the SOLR query features there. It was very difficult, since this is all based on project data, to find a search that I could do to show the results. So I'm doing a very trivial one right here, showing ChemAxon with a wildcard in it. And what I find are there are 48 documents that I have access to that contain the word ChemAxon. And highlighted in red right here is this presentation. And so you see the type of document. You can click on the link to open the document. There are breadcrumbs to where it's located in Google Drive, and you can select any of these breadcrumbs to open up the folder. There's hit highlighting, showing that ChemAxon is bold. You also have facets over here. So shown here, you have the document type and author. And if you were to scroll down, you would actually find the folder locations for the documents. So to summarize, the SOLR search application allows users to find documents by full text search, facet the results to narrow down the hit list, and provides wildcard, regular expression, proximity, and fuzzy searches. But within the context of this application, some of the frequent queries that the users wanted to be able to do was to search for partial corporate identifiers. It's common practice at Genentech for chemists or project teams to represent their molecules with a G followed by the last 4 digits of the molecule. And so one use case that was very important was that to be able to find all molecules such as G star 1, 2, 3, 4. But you can imagine that if I were to do this search, I would find many different documents and many different permutations of the G number G star 1, 2, 3, 4. However, if I have a particular project where there are several thousand molecules, which is typical, if I do the intersection of these two queries, project A and G star 1, 2, 3, 4, provided that that information is in the document, I will most likely find the document that I'm interested in. Another really important use case is project teams want to be able to find key documents or key experiments. So one thing they can type in is HTS, hit follow up for project A. But getting more to the purpose of this this project is I'd like a project team to be able to look across other project teams and find out how they solve certain problems, for example, time-dependent inhibition. So the Techspace Searching works very well and is very powerful and allows project teams to mine and search and mine their data. But there are a number of queries that they cannot perform. For example, a chemist may not know the corporate identifier for a particular molecule, but they may remember something about the structure. So if structure searching were supported, they'd be able to do a similarity search and find the documents of interest. Furthermore, as I mentioned in the beginning, chemistry is represented by embedded ChemDraw or corporate identifiers, which assumes that we have whole molecules. But there is no way to do a substructure search within the text mining. In the future, we're looking to see if we can combine both of these so that I can look for particular problems that a project team has with a given chemical series to see if any other project team has had a problem in that area. But this was the main motivation for us to evaluate document to database. So much of this has been covered already, especially in the previous talk by Daniel about the naming technology. So ChemAxon's naming technology extracts IUPAC names, common names, drug names, SMILES, NG, CAS numbers. And it also extracts embedded structures from ChemDraw, ChemAxon, and Marvin Sketch. For the reasons I mentioned earlier, at this time we're not looking at any of the optical structure recognition, and we're leaving that as a future project. So configuring and running document to database could not have been easier. The first thing you have to do is edit a configuration file. The main thing you have to do is set up your database parameters. And the next thing you need to do is specify a number of different options. For example, I've turned off doing an OSR search, specify a number of threads and the molecule type. That's it for configuring it. Then the next thing you need to do is to run D2DB, the configuration file name, create, in order to create the schema. And then the next line is D2DB, the configuration file index, and you provide it the path to your documents. D2DB will run, automatically extract all of the structures from the documents and deposit them into the database, which can be searched with JChem cartridge. Once you finish the indexing, you can set this up on a cron job so that it'll periodically update the structures. So now we have a way to actually capture the structures, but we needed an application in order to view the results. And I must say that ChemAxon could not have made this any easier. So they had just the applications we needed. First of all, there's Marvin for JS for editing the structures, the query structures. At Genentech, we support both the Mac and the PC and the Windows machines. Supporting the ChemDraw plugin, which we currently use on the Mac environment, has been a real headache. So we were looking for something and a way to get away from that. And as you know, Google is dropping support for the Netscape plugin API. So that's another reason for us to move off of the ChemDraw plugin. So we're currently working on replacing the ChemDraw plugin with Marvin for JS, but we did have a major hurdle in that the chemists required that we be able to copy and paste structures from ChemDraw into Marvin for JS. And realizing this, I contacted our account manager and I pleaded with him to add support for copy and paste as MOL file in ChemDraw, and they have delivered that in ChemDraw 14, so we can proceed with the migration to Marvin for JS. Over the summer, we successfully migrated from the Accord cartridge to the JChem cartridge, and we've noticed a marked improvement in the performance. I've already mentioned document to database and how this has indexed all of our documents to provide the structures. So in order to test this application, I entered in Tamiflu, a Roche product with a drug name, common name, as well as embedded ChemDraw. So as the indexing process goes through, it'll pick up all of these different items and add the structure to the database. So then I can go to Marvin for JS, type in the structure. I'm using the cartridge, so I could have done I could have done substructure, similarity search with all of the different features, but for simplicity, I just did an exact structure search. And here I see the results, which look very similar to the results that I had with the SOLR application. Again, I can see the document type. This was the test document that I used to test D2DB. This is this current presentation. I also have the same facets, author, document type, folder. So if you recall in the beginning, I said that we use embedded ChemDraw as well as corporate identifiers. And out of the box, D2DB does not recognize our corporate identifiers. But working with Daniel, he quickly added support for this within document to database. And so now we can search for and extract structures for our corporate identifiers. And to implement this was actually very simple in our config file. We specify the regular expression for our corporate identifier, and we give it a query that will return the structure given that corporate identifier. So in conclusion, we've indexed 79,000 out of 84,000 documents. There are about 5,000 documents that failed, and after a detailed analysis of the logs, we find out that there are only a few different exceptions that account for most of these documents. We also extracted 150,000 structures. 30,000 of them were based on the corporate identifier. These numbers, however, are actually much lower than expected because many of our documents have the partial G numbers. So while in Techspace Searching it was very useful to have searching for G star 1, 2, 3, 4. With documented database, we actually require the full G number. So I'm currently working with our project teams to see to encourage them to use full G numbers, and many of them are compliant. So this should get better in the future. So basic conclusions about documented DB. It's very easy to configure, very easy to run. And I can't say enough about how wonderful it was working with Danielle and ChemAxon, who were very responsive to all of our requests and questions and sent us frequent updates, patch releases to address some of the issues we were having. And finally, I think that, I'm confident that we could use documented database to enable structure searching across our project team documents. And some future directions are to collaborate with ChemAxon to resolve these exceptions, evaluate Clyde. I did try OSRA, but I was, had a lot of hanging processes. So I'd like to see if Clyde performs better. And finally, I'd like to combine text and structure searching across the project team documents. And with that, I'd like to thank you for your attention and thank Daniel and the ChemAxon team.
So this is really nice. I like it. Have you thought at all about strategies for extracting structures from these partial corporate IDs? I mean, could you go back and find something from context or which project it was from, and then maybe even look and say, okay, well, it's probably the one that has the most data registered, because this is something we've been dealing with too.
Yeah, this is something that we've thought a lot about, but oftentimes in documents you might find multiple projects. And so it's actually a very difficult problem to solve. But I mean, it's something that we're keen on trying to find some kind of solution. Because as you see, we're missing out a lot of structures in the documents.
Thanks for this. Have you thought about enhancing your facets with perhaps putting those regular expressions for corporate identifier or project into the facets themselves? So you might be able to, when you do a search, someone doesn't necessarily ask for corporate identifier, but you get facets on the left.
Yeah, so the problem with that is the facets are actually in the body, and we don't actually have a specific field to capture the corporate identifiers. So if we could do pre-processing and extract them, then we could do something like that.
Well, thanks very much for your presentation. It was very interesting to see your side of the story. First, a quick question is, do you know how many years your document span? So how far back does it go, just roughly?
So maybe 4 years.
4 years, okay.
Yeah.
Mm-hmm. So one of the things we were actually surprised about those cases where it failed. So we've been looking into that, and it was very useful to get some examples. So I want to give some context here. But some of the difficulties we encounter is that all these documents have different versions of Word and different versions of embedded structures from ChemDraw and ChemSketch, which was MDL, CMix, Accelerate, BioVia. So, and actually for this one, we actually, it's a format that's not documented. It's binary and proprietary. So we're actually working very hard, and we hope to make this to support all the cases. So this was really a stress test for us, that it was so many documents, so 85,000, and that's probably several hundred of embedded structures. So, well, it's nice that we have already this, but we are really hoping to have this solution where you can actually get all this chemistry, and we look forward to that in the future.
I must also say that some of the documents are actually password protected, so
right.
That's no fault of ChemAxon, but